Hello everyone and welcome to Unit 5 Chemical Reactions, Section 2, the conservation of matter. And we talked about how chemical reactions occur and we quote-unquote create new substances, but keep in mind that we're not just creating these things out of thin air. All we're doing is really rearranging current things, because you can't just pull matter or mass out of thin air. It has to actually come from somewhere. And so in a chemical reaction, we generally have the idea that everything that goes in must come out. So looking at this graphic that we have right here, on the right hand side, you can see that we have 2 oxygens and we have 4 hydrogens. So those are the products in these 2 waters. Now, in order to get those, we had to have put in that same amount of stuff. So over on the left-hand side, you see that we put in 2 oxygens, and if we had just put in 1 hydrogen on the left-hand side, that would not have been enough, or excuse me, 1 hydrogen molecule, because we then only would have had 2 hydrogens. So we had to add 2 hydrogen molecules to every 1 oxygen molecule. So the general idea here is just that whatever we put in on the reactant side, we will get out on the product side. So we always need to make sure that they are equal to one another. And so like I said on the previous slide, according to the law of conservation of matter, or sometimes called the law of conservation of mass, in chemical reactions, atoms will be rearranged to make new compounds. That's a really important point to be made. We are saying that they are rearranged. We are not saying that they are created or that they are just appearing out of thin air. We're just rearranging current atoms in their current configuration to make new ones. And also, the law of conservation of matter, what it really states, and what the biggest thing you need to get out of this is that it states that matter cannot be created or destroyed. It only gets changed. Now, sometimes people now call this the law of conservation of mass rather than the law of conservation of matter, because in some cases, and we'll talk about when we get to nuclear chemistry, in some cases, matter can actually appear to be destroyed. So it disappears in its current form and it changes directly into energy. Well, it's not really getting destroyed as much as it is just getting changed. So the law of conservation of matter or the law of conservation of mass, they're interchangeable really, explains that it's not getting created or destroyed, only that it is getting changed. So the idea here is that that holds true for everything on Earth, including chemical reactions. So when we're doing chemical reactions, we need to make sure that what goes in must come back out. If you use the analogy of a daycare center, let's say, and let's say I drop off my 2 children. Here's one. They're not the cutest children, but they are. Oh, that one's got a big head. That's okay. Everyone is created equal. They're all beautiful. But we have 2 children that get dropped off at the daycare center. And then at the end of the day, the daycare teacher comes out and she says, okay, here is your child. Well, I can tell that it's the big-headed one, but there's a problem. I dropped off 2 children, and I am now giving back 1 child. That is a problem. Okay, so just like in Child Protective Services, the same holds true in a chemical reaction. Whatever goes in must come back out. So we are not going to drop off 2 children at daycare, get 1, and think that everything is okay, because it is not. We are going to have a lawsuit, as well as probably having to find a new daycare center. Now, in chemical reactions, we don't just hold a lawsuit anytime something doesn't show up. So in chemical reactions, what we do is we balance the equations. Okay? So really, we are essentially making sure that everything on the left-hand side, the number of everything on the left-hand side, is going to be even with the number of everything on the right-hand side. So we just want to ensure that both sides of the equation are equal. Now, in order to figure out the number of each atom on each side, we have to look at the numbers that are actually in the chemical reaction. So when we're balancing an equation, we need to make sure that we are counting how many atoms are actually present. So we're looking for these 3 things. We're looking for subscripts, parentheses, and coefficients, because those are going to tell us how the numbers are being distributed. So in this case, we have H2. Okay? The little 2 on the bottom of the H is telling us that there are in fact 2 hydrogens in that molecule. We have O2. The 2 is telling us we have 2 oxygens. And over here, this is telling us we are going to have 2 hydrogens and 1 oxygen. Okay? So the subscripts are important for telling us a lot about exactly how many atoms are in the particular molecules that we are dealing with. If there's no subscript, we assume that it is 1. Okay? Not a negative 1, just a 1. But we assume that it is 1 if there is no subscript. Let me just fill that in so it disappears. Yay, nothing happened. Parentheses we look for because sometimes, like say you have barium nitrate. Okay, and we remember that that 2 is indicating that we have 2 of everything on the inside. So really what that's saying is that we have 2 nitrates, and a nitrate is NO3, so we actually have 2 nitrogens and we have 6 oxygens. Okay, so just kind of think about a nitrate being something that is attached and it doesn't really look like this, but just go with it. A nitrogen with 3 oxygens and we have 2 of them. Well, then if we were to count those up, we have 2 nitrogens and 6 oxygen. Okay? Coefficients are the numbers in the front. This is getting kind of messy, so I'll change color. Coefficients are these numbers out front, and they are distributing to everything in the actual molecule, only that they are attached to. They do not distribute out to the entire problem. They only go to that number that they're attached to. And so that's the same way in math. If you have something like 2x plus 4, you don't suddenly think, oh, I'm going to multiply that 4 by 2. No, it's just the x that gets multiplied by 2. The 4 is kind of staying by itself in that case. So breaking these down a little further and looking at some examples, subscripts are the small size numbers that appear after the element symbol, and they are referring to the element they are just behind. So in this case, we have 2 hydrogens and 1 oxygen. Down here, this one's a little bit tricky, because if you notice, we have a nitrogen here and a nitrogen there. So how many nitrogens do we have? 2. If you weren't tricked by that, then just keep on trucking, because you're doing good. We have a 4 behind the hydrogen. That subscript is telling us that we have 4 hydrogens. And a 3 behind the oxygen. There's no other oxygen, so there's only 3. Again, pretty simple. Parentheses are used to kind of group elements together. And we use what we call the distributive property when we use parentheses. So that 2 is indicating that everything on the inside, the oxygen and the nitrogen, are getting it multiplied by 2. The calcium is not in the parentheses, so according to the distributive property, it is not going to have anything to do with that 2. So we only have 1 calcium. If it had had a subscript, we might have had more, but it doesn't. So we're only dealing with 1 calcium. The nitrogen, again, the 2 has distributed to that nitrogen, so that means we have 2 nitrogens. 2 distributes to the oxygen. 2 times 3 is 6. And again, remember that this is an actual object. Nitrogen, O, O, O. And if I say, oh, there's 2 of those, O, 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 then I can actually count 1, 2, 3, 4, 5, 6. Okay, there's 6 oxygens. So if you're getting confused with the distributive property, then just kind of actually draw it out or imagine it and count up how many there are. In the next problem, looking first at magnesium, there's a 3 behind it. It is not in parentheses. There is no coefficient, so it is just 3 magnesiums. The 2 over here distributes to the phosphorus, so we get 2 phosphoruses, or phosphori, or whatever. Oxygen, 2 times 4, gives us 8 oxygens. Now, coefficients are slightly different than the numbers outside parentheses, just because they distribute to the whole problem. So they're essentially like putting a number on the outside of parentheses for an entire problem. So for this one, we take the 3 times 1 for calcium gives us 3. Then if we said, oh, 3 times n, oh, well, that's, or excuse me, 3 times 1, that's 3. But keep in mind, this nitrogen is already being multiplied by 2. So if we say, oh, there's 2 nitrogens, and I want 3 copies of that, well, then I have 6. 2 times 3 is 6, times 3 is 18. So again, we're just counting up things here, and the coefficient is the number that goes out front, and it distributes to the whole problem. In the bottom one, this one gets kind of messy, but it is not that hard. 5 times 1 is 5. 2 times 2 is 4. Times 5 is 20. 2 times 3 is 6. Times 5 is 30. 2 times 2 is 4. Times 5 is 20. So we're just doing basic math here, just adding up things and multiplying when we need to distribute. So don't get confused by that, because it will get a little bit more in depth, so I don't want you to get lost at this stage. Now what I'd like for you to do is go ahead and answer questions 1 through 6 on your practice problems. I'm going to be posting a key, so if you want, you can pause the video now, do 1 through 6, and then check the key online, then come back and start up from the video at this point. Okay? So go ahead and do it. You can do it. You'll be great. Okay, I'll see you in a minute. Okay, hopefully you did great on your practice problems 1 through 6, and you are ready to move along. So now that we've kind of focused on how we count up atoms in particular molecules, we're now going to look at looking at the entire equation. So the entire equation, when we figure out how many atoms are on each side, is what we call a balanced equation, or rather when we fix the number of atoms on each side, we call that a balanced equation. And a balanced equation is really a recipe. And if you think about a recipe, you know, when you're talking about, say, a cake takes 2 cups of flour and 2 eggs, and on the other side you get a cake. Okay, that is the recipe for a cake. And if you were to say, I'm going to use a 1/4 cup of flour and 10 eggs, and I assume I'm still going to get 1 cake. Well, guess what? You're not. You're going to get a disgusting omelet. Okay, the omelet is going to be filled with flour, which is not going to be very good, but you are going to have a ton of eggs, which is really just making scrambled eggs. Okay, so the recipe has to be even. You have to make sure that what you're putting in is equal to what you're going to get out. So a balanced equation does 2 things. It tells you what the reactants are and how much to mix together. So it tells you, okay, you need 2 calciums and you need 1 phosphate to make whatever the case is. And that's not the actual recipe, but it's just telling you exactly what you need to put together. It's also going to tell you exactly how much you're going to get out. If I'm going to throw 1 cup of flour and 2 eggs into a pan and expect to have enough cake to support an entire army, then number 1, I'm delusional. Number 2, I'm wrong, because that's not what I'm going to get out. So think of this as a recipe. You always have to think about what you're putting in and how much you're going to get out. So there are, of course, some rules when you're balancing equations, and the first one, and the most important, is only add coefficients. Never subscripts. Do not add subscripts. And if you recall, I told you guys previously, when you have like a person, and a person generally comes with 2 arms and 2 legs, okay? Generally, and that's not always the case, but that's usually what we kind of associate with that. And if you think about something like H2O, and let's say that O is body and H is legs, okay? I can't just say, I need to balance this out, so I'm just going to change this to H4O, okay? Because then you're going to get some monster thing with legs coming out of everywhere, okay? We can't just do that. You have to think of this substance as being an actual substance, and if you change the ratio on it, then you're going to get some mutant monster, and that's just not what we want, okay? So don't add the subscripts. Do not change those numbers on the bottom. Only add coefficients. So I'm not going to say, well, I need 4 hydrogen, so I'm just going to change it to 4. I would say, what about if I just add another water? Because then I would have 4 hydrogens, okay? So I could take hydrogen and multiply it by 2, and that would give me what I need, rather than trying to change it into some sort of horrible, deformed, mutant monster with 6 legs, okay? One tip to try to do, never try to balance oxygen first. Oxygen's kind of a diva, and it's really just going to get messy. Oxygen, has that -2 charge, and whenever it goes into formulas with things, that charge kind of creates a weird ratio with other substances. Now, what usually happens is if you balance everything else first, 99% of the time, oxygen will just fall into place, and it'll just become balanced some magical way, and you're not really sure how, but it just happened. So just trust that that's going to happen. If it doesn't, then the last step would be to balance out the oxygens. The last thing is that coefficients need to be whole numbers. You couldn't have taken this H2O up here and say, well, I need 3 hydrogens, so I'm just going to multiply this by 1.5, okay? Again, you cannot have 1.5 humans, so you cannot have 1.5 molecules, okay? Think of them as full structures. They have to be all together in order to function. So the first step when you're balancing an equation is to take the unbalanced equation and kind of add up what you have on each side. Recalling, and a lot of times I will recommend to people that you do actually draw an arrow straight down the center, because that helps sometimes. remembering that that arrow in the middle, or excuse me, a line straight down the center, that arrow in the middle is indicating that this is the reactant side and this is the product side. So the reactant side, this is what's going to go in on this side, and this is what we're going to get out. And all we're trying to do is say that everything we put in, we get out. Remember our children at the daycare. If I put this in, I better get them back out, or we're going to fight. Okay? So on the left-hand side, we want to count up everything we have to see if we're balanced on the other side. First thing is carbon. Okay? On the left-hand side, it is not in parentheses. It does not have a coefficient. There is no number behind it, so there's just one carbon. I would check the entire side. Okay? So I'm looking here, one carbon, no carbons here, so just one carbon. I then have hydrogen. Hydrogen has a 4 behind it. Again, no parentheses. I check over here, no hydrogen, so just 4 hydrogens. Oxygen, 2. I would check this molecule. This one has no oxygen, so just 2. On the right-hand side, carbon, 1. Again, check this one, no carbons, so we're good. Hydrogen is the next one, so let's just do hydrogen again just to keep them even. On the right-hand side, I have 2, none right here. Oxygen, I have 2 here and 1 here. Okay, so I just add that up. Remember, I'm actually trying to figure out how many oxygens I have. Up here I have 2. Right here I have 1. How many oxygens is that? 3. It's also a face. I don't, there's a nose. Anyways, so we have 3 oxygens on the right-hand side, and so that is what we put here. Now, if we look at that, that's not balanced. Checking first with carbon, carbon is balanced, 1 and 1. On the left, though, hydrogen, we have 4. On the right, 2. How can I make 4, or how can I make 2 become 4? Yes, you're correct. You can multiply it by 2. I'm just pretending you're here. 2. So that 2 then distributes to the hydrogen. I now have 4. I now have 2 oxygens here. Over here, I also have 2 oxygens. So when I add those up now, I have 4. So notice that when I add this coefficient right here in front of H2O, because it's not a pure element, it's going to affect the hydrogen and the oxygen numbers. So do not forget to kind of recheck and see what changed. Again, I had 2 over here. I now have 2 over here, so that's like this, which is now some monster, but whatever. So I now have 4 oxygens. On the left-hand side, I only have 2, so what can I do to that one? Right here, noticing that there's no oxygen here, so this is the only oxygen, the one I need to adjust. So in order to fix that one, I can add a 2 there. That's going to distribute, changing that to 4. Then I check, carbon is good, hydrogen is good, oxygen is good, so we're good. Okay? And of course, I'd already done it down here, so you can see what I did. I just wanted to go through the process. Okay, and then the last example I'm going to show you here, this is probably the hardest example that you will ever see in your entire lives, because it involves doing some kind of multiplication on both sides. And so to start, we have the reactant side, of course. We have the product side. I'm going to draw a line down the middle just so we can remember that that is where we are kind of breaking apart the reaction. On the left-hand side, I have a 2 right here, so that means I have 2 aluminums. 3 right there means I have 3 oxygens. On the right, I have 1 aluminum because there's no number written behind it, and I have 2 oxygens. Okay, so I want to figure out how to work this out. Now, keep in mind, I may end up having to change things. It's okay if I do. So let's start with aluminum. We don't want to start with oxygen because oxygen, like I said, is always funky. Sometimes it messes things up, sometimes it doesn't, but we'll just start with aluminum. So on the left, I have 2 aluminums. On the right, I have 1. I can fix that by making this 2. So that changes this to 2. Okay. Now I look at oxygen. I have 3 on the left. I have 2 on the right. Well, there's no even number that I can get one of those. I can't multiply 2 by something to make it 3. I could if it was a fraction, but I can't do that. I have to stick to whole numbers. So what I have to do here is actually figure out what their least common denominator, or least common multiple is, rather. Between 2 and 3, the least common multiple of both of those is going to be 6. So how do I get from 2 to 6? Multiply it by 3. So that changes this one to 6. How do I get from 3 to 6? Multiply it by 2. That changes this to 6. But what does it also change? Notice I put a coefficient. A coefficient multiplies by everything in the problem. So it distributes to the oxygen. It also distributes to the aluminum. So that changes aluminum to 4. So initially, we thought we were going to be good with 2 on the right-hand side for aluminum. But now what we see is that that is not sufficient. We actually need to place a 4 in front of the aluminum to balance out the left-hand side with the right. And that's okay. It is not the end of the world to have to erase. Now, of course, it is if you're doing it in pen, but use a pencil when you're practicing these in the beginning until you get the hang of it, because it's not the end of the world to have to adjust that. So at the end now, we check, aluminum is good, oxygen is good, we are good. Okay, I hope that this has helped you a little bit, and I hope that you are set with balancing. When we get back to class, of course, we will do some practice and run through your practice problems, the rest of them if you can, and if you do, then I will have some stuff that you can go ahead and get ahead on in class. If not, then we can work together just like last time, and I will see you guys next class. Bye.